When we talk about generative models, we are talking about a family of machine learning systems whose goal is not just to recognize patterns in data, but to create new data that resembles what they have seen before. If you train a generative model on text, it can produce new sentences or documents that sound like the training material. If you train it on images, it can produce new images that look as if they came from the same distribution. If you train it on audio, it can synthesize speech or music that reflects the patterns in the original recordings. The key idea is that instead of only learning to classify or predict labels, these models learn the underlying structure of the data itself. To understand generative models deeply, it helps to start with a basic distinction in machine learning between discriminative and generative approaches. A discriminative model focuses on learning a boundary between classes or learning a direct mapping from inputs to outputs. For example, if we train a classifier to detect spam emails, the model learns a function that maps an email to a probability of being spam. It does not need to understand how emails are written in general. It only needs to find features that separate spam from non-spam. In contrast, a generative model attempts to model how the data is generated. It tries to learn the probability distribution over the data itself. Instead of just saying this is spam or this is not spam, a generative model could, in principle, generate new spam-like or non-spam-like emails because it has learned something about the structure of language used in those categories. At the heart of generative modeling lies the concept of probability distributions. Real-world data is not random noise. It follows patterns. In text, words follow grammar, semantics, and context. In images, pixels are not independent, they form edges, shapes, textures, and objects. A generative model tries to approximate the true, unknown probability distribution that produced the observed training data. We often denote the true distribution as P_data X, and our model defines its own distribution P_model X. Training the model means adjusting its parameters so that P_model X becomes as close as possible to P_data X. This idea of closeness is formalized using measures such as likelihood and divergence. In maximum likelihood training, we choose parameters that maximize the probability of the observed data under the model. If our dataset contains samples x1, x2, xn, we adjust parameters to maximize the product of P_model 11 over all I. In practice, we maximize the sum of log probabilities because it is numerically more stable and mathematically convenient. This process encourages the model to assign high probability to real data. If the model successfully approximates the data distribution, then sampling from P_model X will produce realistic new examples. One of the simplest classes of generative models is the family of autoregressive models. In autoregressive text models, the joint probability of a sequence of words is decomposed into a product of conditional probabilities. Suppose we have a sequence of tokens W1, W2, wait. The probability of the entire sequence can be written as the probability of the first token times the probability of the second token given the first, and so on, until the probability of the last token given all previous tokens. This decomposition allows us to model complex sequences by predicting one token at a time. During training, we feed the model real sequences and train it to predict the next token at each position. During generation, we start with an initial context and repeatedly sample the next token from the predicted distribution, appending it to the sequence. Modern large language models are autoregressive generative models built on architectures such as the transformer. The transformer architecture introduced the idea of self-attention, which allows the model to weigh the importance of different tokens in a sequence when producing representations. Instead of processing text strictly left to right with recurrent connections, transformers process sequences in parallel during training and use attention mechanisms to capture long-range dependencies. The generative capability arises because, at inference time, the model uses its learned conditional probabilities to sample tokens sequentially. Another major class of generative models is based on latent variables. The intuition here is that observed data is generated from some underlying, lower-dimensional factors that are not directly observed. For example, an image of a face might be generated from latent variables representing identity, expression, lighting, and pose. A latent variable model introduces a hidden variable z and defines a joint distribution over observed data x and latent variable z. The model specifies how z is distributed and how x is generated from z. Training such models involves learning both how to infer z from x and how to generate x from z. Variational autoencoders, or VAs, are a well-known example of latent variable generative models. A VA consists of two main components, an encoder and a decoder. The encoder maps input data to a distribution over latent variables, typically parameterized as a Gaussian with a mean and variance. The decoder maps a latent sample back to the data space, reconstructing the input. The training objective combines two terms, a reconstruction loss that encourages the decoder to reproduce the input accurately, and a regularization term that encourages the latent distribution to stay close to a prior distribution, often a standard normal. This regularization is expressed as a divergence between the encoder's output distribution and the prior. The key innovation in VAs is the use of variational inference to approximate intractable posterior distributions. In many latent variable models, computing the true posterior distribution PZ vertical bar x is difficult. VAs introduce a tractable approximate posterior QZ vertical bar x and optimize a lower bound on the log likelihood of the data, known as the evidence lower bound. This allows efficient gradient-based training using backpropagation. Once trained, we can generate new data by sampling z from the prior distribution and passing it through the decoder. Because the latent space is structured and continuous, VAs also allow smooth interpolation between data points. A different and highly influential class of generative models is generative adversarial networks, or GANs. GANs consist of two neural networks, a generator and a discriminator. The generator takes random noise as input and produces synthetic data samples. The discriminator takes either real data or generated data and tries to distinguish between them. The two networks are trained in a minimax game. The generator tries to produce samples that fool the discriminator into believing they are real. The discriminator tries to correctly classify real versus fake samples. This adversarial process, the generator learns to produce increasingly realistic outputs. The training objective of GANs can be seen as minimizing a divergence between the model distribution and the data distribution, but indirectly through the discriminator. In the original formulation, the discriminator outputs a probability that a sample is real. The generator aims to maximize the probability that the discriminator labels its outputs as real. In practice, training GANs can be unstable. The dynamics of two networks competing can lead to oscillations, mode collapse, or vanishing gradients. Researchers have proposed many variants, such as Wasserstein GANs, to address these issues by changing the loss function and improving training stability. Diffusion models represent another major breakthrough in generative modeling, especially for images and audio. The core idea of diffusion models is to define a forward process that gradually adds noise to data over many time steps, eventually transforming it into pure noise. Then, a neural network is trained to learn the reverse process. Starting from noise, it gradually denoises the sample step by step to recover a structured data point. The forward process is fixed and known. It typically adds Gaussian noise according to a predefined schedule. The reverse process is learned by training a model to predict either the noise added at each step or the original clean data. Diffusion models can be interpreted as learning to approximate the score function, which is the gradient of the log probability density with respect to the data. By learning this score, the model can perform a stochastic reverse diffusion process that generates samples from the data distribution. One advantage of diffusion models is their training stability compared to GANs. They are trained with a straightforward regression objective rather than a minimax game. Although sampling can be computationally expensive due to many iterative steps, recent research has significantly reduced the number of steps required. Across these different architectures, a unifying theme is that generative models must capture high-dimensional probability distributions. Real-world data often lives in very high-dimensional spaces. For example, a 256 by 256 RGB image has nearly 200,000 dimensions. Modeling a full joint distribution in such a space is challenging because the number of possible configurations is astronomically large. Generative models rely on neural networks to learn structured representations that capture dependencies among dimensions. They exploit the fact that real data lies on or near a lower dimensional manifold within the high dimensional space. The method of sampling depends on the type of model. In autoregressive models, sampling is sequential and straightforward, repeatedly sample from conditional distributions. In BAS, sampling involves drawing a latent variable from the prior and passing it through the decoder. In GANs, sampling is as simple as feeding random noise into the generator. In diffusion models, sampling involves running the learned reverse diffusion process starting from noise. The quality and diversity of generated samples depend both on the learned distribution and on the sampling strategy, such as temperature scaling or guidance methods. Temperature is an important parameter in generative text models. When sampling from a probability distribution over tokens, we can adjust the distribution by dividing logits by a temperature parameter before applying softmax. A low temperature sharpens the distribution, making high probability tokens even more likely and leading to more deterministic outputs. A high temperature flattens the distribution, increasing randomness and diversity but also the risk of incoherence. Techniques such as top-K sampling or nucleus sampling further constrain the sampling process to the most likely tokens, balancing creativity and reliability. Evaluation of generative models is a complex topic. Unlike classification tasks, where accuracy is a clear metric, generative tasks involve subjective qualities such as realism, diversity, and coherence. For image models, metrics like the Fresh-A inception distance attempt to measure the similarity between distributions of real and generated images using features from a pre-trained network. For language models, perplexity measures how well the model predicts held-out text, reflecting its ability to model the underlying distribution. However, perplexity does not directly measure qualities like factual correctness or long-range coherence. Human evaluation often remains important.
If you find this video exciting, please like, subscribe, and turn on notifications. See you in the next AI for Beginners educational video.